what free oscillations are. A child swinging without someone pushing her, or a simple pendulum that is displaced and released are examples for free oscillations. Without an outside force acting on either of them, the amplitude of their swing would gradually decrease, and both the systems would eventually come to a halt. There are dissipative forces that do not allow the oscillations to sustain, and they get damped. But if the child in the swing applies a push by pressing her feet to the ground periodically, the oscillations can be maintained and the amplitude can also be increased. Now, the free oscillation of the swing becomes forced or driven. In a system with such forced oscillations that are governed by a harmonic force, two angular frequencies should be considered. The natural angular frequency omega, which is the angular frequency of the system at which it would oscillate if it were displaced from an equilibrium position. The angular frequency omega d of the external force that causes the forced oscillation. Now, let us assume an external force Ft of amplitude f0. The amplitude varies periodically with time. Such a force, if applied to a damped oscillator, can be written as Ft equals f0 cos omega dt. Here, the motion of a particle which is under the combined effect of a linear restoring force, a damping force, and a driving force dependent on time can be represented as MAT equals minus kxt minus b nu t plus f0 cos omega dt. Acceleration can be substituted by d square x by dt square, and the above equation now becomes md square x by dt square plus b dx by dt plus kx equals f0 cos omega dt. In this equation, m is the mass of the oscillator on which an external force of angular frequency omega d is applied at a periodic interval. Initially, the oscillator would oscillate with a natural angular frequency of omega. When a periodic external force is applied, the oscillations with the natural frequency gradually die out, and oscillations with angular frequency of the external periodic force replace them. The displacement after the natural oscillations die out can be written as xt equals a cos omega dt plus 5. Here t is the time measured from the moment we apply the periodic external force. A is the amplitude, and it is a function of the force frequency omega d and natural frequency omega. It is given by A equals f0 by m square into omega square minus omega square d whole square plus omega square d b square whole to the power of half, and tan phi equals minus nu naught by omega d x naught. Here m is the mass of the particle, nu naught is the velocity, and x naught is the displacement at time t equals 0. This time is the moment in which the periodic force is applied. The above equation shows how the amplitude is dependent on the angular frequency of the driving force. We look at two different scenarios concerning such an oscillator. One in which the force frequency, omega d, is far from the natural frequency omega, and another in which it is close to it. A. Small damping, driving frequency far from natural frequency. In a case like this, omega dB will be much smaller than m into omega square minus omega square d, so we can neglect that term. The previous equation for amplitude becomes A equals f0 by m into omega square minus omega square d. The following figure demonstrates the dependence of the displacement amplitude of such an oscillator on the angular frequency of the driving force for varied amounts of damping present in the system. The amplitude is the greatest when omega d by omega equals 1. The 5 curves correspond to different extents of damping present in the system. Curve A shows least damping, and it increases successively in curves B, C, D, and E. The peak seems to be shifting towards left with increasing B. When we change the driving frequency, the amplitude tends to infinity as it nears the natural frequency. We must remember that this is an ideal scenario. In a real system, you're unlikely to find zero damping. We can experience it while swinging, when we time our push perfectly with the time period of the swing. The swing gets the maximum amplitude. The amplitude is large, but it is not infinite. Something is always damping it. We can see it in the next scenario. Driving frequency is close to natural frequency. In cases where omega d is very close to omega, m into omega square minus omega square d will be much smaller than omega dB. For a reasonable value of b, the amplitude becomes A equals f0 by omega dB. Here, the maximum possible amplitude for a given driving frequency is directed by the driving frequency itself and the damping. It is never infinity. we see that the amplitude increases when the driving frequency is close to the natural frequency. This phenomenon is called resonance. The swing is a good example of where one might experience resonance. The skill in swinging the swing to greater heights depends on one's ability to synchronize the rhythm of pushing with the natural frequency of the swing.
Older cars, when driven at certain speeds, tend to exhibit vibration of the chassis because the frequency of vibration of the vehicle equals the natural frequency of the chassis at those speeds.
Let's understand this better. We have a set of 5 simple pendulums of assorted lengths. All are suspended from a common rope, as shown here. Pendulums 1 and 4 have the same lengths. Other pendulums have different lengths. When we set pendulum 1 into motion, the energy from it gets transferred to the others through the common rope, and they all start to oscillate. Here, the driving force is provided through the connecting rope. The frequency of this force and the oscillating pendulum 1 is the same. Pendulums 2, 3, and 5 start oscillating with their natural frequencies and have different amplitudes. The motion is gradually damped and it does not sustain. The frequencies of oscillation also change, and they finally start oscillating with the same frequency as pendulum 1, which is the frequency of the driving force. Yet their amplitudes are smaller. Pendulum 4, however, behaves differently as it oscillates with the same frequency as pendulum 1, and the amplitude gradually picks up. It soon becomes very large. Here we observe resonance. The natural frequency of the system coincides with the frequency of the driving force.
Resonance can be both useful and dangerous for us. Guitarists make use of resonance to produce sharp notes. The destructive effect of resonance can be understood fully if we are to look at the case of the Tacoma Narrows suspension bridge. Winds blowing across the bridge frequently induced vibrations in it, which were close to the natural frequency of the bridge. The bridge was finally set in resonance on the 7th of November 1940 due to heavy crosswinds, and after resonating for a while, broke apart and collapsed. Soldiers marching on bridges are specifically told to stop marching so that the frequency of their marching does not set the bridge into resonance.
During earthquakes that cause massive destruction of life and property, it is interesting to observe that sometimes short and tall structures remain unaffected, while the medium-height structures collapse. This happens because natural frequencies of short structures are higher, and those of taller structures are lower than the seismic waves. The mid-height buildings have frequencies nearly in the same range and get affected the most. Aircraft designers make sure that the natural frequencies at which the wings oscillate never matches the frequencies of its engines during a flight. An error here can be devastating.
Damped, simple harmonic motion. We have said in previous sections that ideal simple harmonic motion is not possible in the practical world. This is because all oscillations eventually die out with time, and the system eventually comes to rest. This means that even as it is oscillating, something is causing the system to bleed energy. But what causes the system to lose energy in such continuous fashion? Friction is the major reason for this. As we know, air has some density, and this density opposes movement through it, causing friction and hence loss of energy. The string by which a pendulum is suspended may not be perfectly unstretchable, leading to losses. Springs may also have their own spring constant, which opposes deformation in the first place. This process of decaying of oscillations is known as damping, and such oscillations are known as damped oscillations.
To understand this better, let us consider a system as shown in the visual. A block of mass m oscillates vertically on a spring. The spring constant of the spring is K. O represents the equilibrium position of the block under the influence of gravity, and X represents the displacement from O. The block is connected to a vane which is submerged in a liquid through a rod. The vane and the rod are assumed to be massless here. As the block of mass oscillates up and down, the vane also moves along with it inside the liquid, displacing it. The liquid in turn exerts an inhibiting drag force on the vane and consequently on the system itself. The mechanical energy of the system decreases with time. as it gets transferred to the thermal energy of the liquid and the moving vein. We can term the damping force exerted by the liquid on the system to be Fd. The magnitude of the damping force is proportional to the velocity v of the vein or the block. The force acts in a direction opposite to that of the velocity. This is considered to be true only when the vein is moving slowly. In that case, we get Fd equals minus Bv. Here, B is the damping constant and is dependent on the properties of the liquid used. The negative sign signifies that force and the velocity are opposite to each other. From position O, which we know is the position of equilibrium of the block, the displacement is denoted as x. The restoring force on the block due to the spring is Fs equals minus kx. Therefore, the total force acting on the mass becomes F equals Fs plus Fd equals minus kx minus bv. Let us consider acceleration at of the mass at time t. Then, applying Newton's second law of motion for force components along the x-axis, we get mat equals minus kxt minus b nu t. We assume that the motion is one-dimensional and hence we do not use vector notation. Now we substitute velocity nu t with dx by dt and acceleration at with d square x by dt square to get the following equation. M dx squared x by dt square equals minus kx minus b dx by t square. Md square x by dt square plus kx plus b dx by dt equals 0. The solution of this equation would give us the motion of the block under the influence of a damping force. This force is proportional to the velocity. After integrating, the solution is found to be xt equals a e to the power minus bt by 2m cos omega dash t plus phi, where a is the amplitude and omega dash is the angular frequency of the damped oscillator. The expression for the angular frequency is omega dash equals square root of k by m minus 4m squared. Option omega dash equals root k by m minus b square by 4m squared. The cosine function has a period 2 pi by omega dash. The function xt is not periodic because the factor e raised to minus bt by 2m decreases continuously with time. However, for a small decrease during one time period t, the motion represented by the equation is approximately periodic. The visual graphically shows this solution. It represents displacement as a function of time in damped harmonic oscillations. The damping increases successively from curve A to D. The solution can be regarded as a cosine function with amplitude a e raised to minus bt by 2m. This amplitude gradually decreases with time. Assuming there is no damping, that is b equals 0, the equation xt equals a e raised to minus bt by 2m cos omega dash t plus phi becomes xt equals a cos omega dash t plus phi, which is the equation for simple harmonic motion and expresses the displacement in an undamped oscillator. Also, the equation omega dash equals root k by m minus b square by 4m square becomes omega dash equals root k by m, which is the expression for the angular frequency of an undamped oscillator. We had seen earlier that mechanical energy of an undamped oscillator is constant and given by the equation E equals half ka square. In a damped oscillator, the mechanical energy decreases with time. For small damping, we can find Et by substituting A with A e raised to minus bt by 2m, which is the amplitude of the damped oscillation in the above equation. We get E equals half ka square e raised to minus bt by m. This equation shows the total energy of the system decreases considerably with passing time. For small damping, the dimensionless ratio, B by root k by m, is much less than 1.